We are at the dawn of a new age of high-precision gravitational experiments. Most proposals for such experiments have one thing in common. They rely on a notion of length. However, in general relativity, there is no unique concept for the length of a system. In our article, Frequency Spectrum of an Optical Resonator in a Curved Spacetime, we addressed the conceptual problem of length for a subset of experimental proposals. We establish a model for an optical resonator consisting of two mirrors attached to a rod which is supported somewhere between the two mirrors. The support is used to direct the resonator. Using this basic model, we clarify the meaning of two different concepts of length in general relativity: radar distance and proper distance. Radar distance is defined as the time a pulse needs for a round trip between the two mirrors multiplied by the speed of light and then divided by 2. We explain how the radar distance is directly related to the frequency spectrum of the optical resonator. Proper distance is a geometric distance, measured along a spacelike curve. It gives the length of a rigid rod. Our main results are the explicit expressions for the relative change of the frequency spectrum for an optical resonator in a weakly curved spacetime. First, we derive the relative change of the frequency spectrum of a rigid resonator dependent on acceleration, curvature, the displacement of the support, and the position of the frequency measurement. Then we extend the description to a deformable rod. The deformation of the resonator depends on the speed of sound in the material it is composed of. A resonator is rigid when the speed of sound is infinite. A notion of causal rigidity is obtained for the speed of sound approaching the speed of light. As a first example calculation, we analyze the effect of uniform acceleration, neglecting curvature. As a second example, we consider the free fall towards a spherical body that could be the Earth or a black hole. As a more down-to-earth example, we consider the optical resonator in front of a small moving sphere. The article is written in a clear, self-contained and pedagogical way to make it easily accessible for a general audience. We hope our results will help to generate new exciting experiments in the field of gravitational physics.